Next talk will be Malek Abdesselam on field theoretic cluster expansions in the Brydges-Kennedy forest sum formula.
Thanks, John. Okay, so I'll do it the old-fashioned way. First, I would like to dedicate this talk to the memory of Pierre Leroux. The title is about field theoretic cluster expansions and the Brydges-Kennedy forest sum formula. Actually, this is what David just talked about under the name of Abdeslam, but we call it Brydges-Kennedy formula.
Sorry, can you turn your mic on?
Okay, so first I'll give you the outline of this talk. So there is the word field theory. So quantum field theory. What is quantum field theory? That's what I'm going to start with. And nothing I will say will make sense. So after that, I'll feel bad, and we'll try to do a little bit of mathematics. And I'll talk about Mobius inversion in partition lattices, then decoupling, or what we call the cluster expansion, this operation of trying to factorize the Z that David talked about. And finally, I will try to present proofs of this Brydges-Kennedy forest formula, and the subsections go proof number 1, number 2, etc. That was the title of a talk I gave when I went to Montreal, thanks to the invitation of Pierre in 2004. Okay, so what is quantum field theory? Okay, so there is lots of different possible answers to this question.
Maybe you can make it bigger. Yeah, it's not a focus. It's a little bit, sorry to bother you.
You want it bigger?
Focus. But it's much better, yes. Yes, already much better.
Okay.
Now we are
Okay. Okay, so as I said, there are several possible answers to this question. The answer I'm going to give you reflects my favorite point of view, but it's not the only one. So for me, it's measure theory in function spaces. So phi will denote a function from Rd to R, but we call that the field. Capital F is your favorite vector space of functions, your function space. Then I is a function from this F into R, which is a function of functions, usually called a functional. And d nu is a probability measure on this space F. And I want the probability measure to look like in the formula here. So the integral, or the expectation with respect to this probability measure of I, is a ratio where you integrate d phi over this vector space F, and you integrate the functional I times a certain weight here, which is like a Boltzmann weight, exponential minus some function of the field. D phi here, well, this is the usual notation for Lebesgue measure, except it's on F. So that means you have product over x in Rd of the differential of phi of x. So it's not a differential with respect to x. X is just a label for the variable phi of x. And S of phi, this is called the action functional. And I wanted to have this particular type of form, integral over Rd of the square of, 1/2 the square of the gradient of phi at x, the square of phi, and also an extra term, which is lambda times the 4th power of phi, and I suppose that this lambda here is actually a small parameter, so I'm trying to perturb around the situation given by this. So this is the action functional, and as you see, it's the integral over space of a local density, so a function which only depends on what's going on at the point x and involves the field phi, and let's say the first derivatives of this field. Okay. So why look at this? Well, it's extremely natural from a mathematical point of view because, okay, if you're either doing algebra or analysis, if you're doing analysis, you probably do PDEs. And if you want to go a little bit, explore other domains from PDEs, well, this is a natural thing to look at because if you look carefully here between the -1 and s, there is a factor of 1, which is very large. And therefore, you can approximate this by the evaluation of this integral at the critical points of this action functional that by Laplace method or stationary phase method. And if you do this, you have to solve for the derivative of s with respect to phi is equal to 0. And if s looks like this, usually it's a PDE. So, okay. If you want to understand a measure like this, one way to do it is to know what are the moments of this measure. So this would be integrations of products of things like this. That means you take test functions f1, fn. This is just the distributional pairing, and take products and look at the expectation. If you know all these things, in principle, you know the measure. Okay. All right. Another thing is the notion of connected correlation functions or cumulants. So there are new collections of multilinear functionals, Cn instead of Sn, and they can be defined in this way. So actually, we know the left-hand side, but this is also a definition for the right-hand side because, okay, if we know C1, then we can get C2 by putting these guys on the other side, etc. So there is a defining property, which is that the moments, the correlation functions Sn are given by sums over partitions of the set 1 to n, product over the blocks of this partition of the cumulants or connected functions only involving the guys in that block. Okay, and you can go from this to a formula for the Cn in terms of Sn, and this is Mobius inversion in the partition lattice, and the correct formula is this.
This partition lattice is refined as it's the lattice of set partitions.
Yeah, set partitions, not integer partitions.
Yes, and the relation is that one is a subdivision of the.
I'm going to talk about
Yes,
this.
yes.
This is just a preview. Okay.
And the formulas on the first slide are meaningless, but that's not a real problem.
No.
Combinatorial is okay.
So just terminology, well, I guess you know this by now. The partition function is just the integral over this, is the integral without the observable I of phi. The pressure is log z divided by the volume of Rd. The endpoint function is, I don't know if it's really the standard definition, but you can expand this by multilinearity, and it gives you this, which involves this kernel. So this is the kernel of this multilinear functional involving points at locations x1, xn in Rd. And you can ask the following questions. Is my quantum field theory d nu non-trivial? That means it's not a Gaussian measure. Usually you test that by the non-vanishing of cumulants of order 3 and above. For the model I showed, it starts at 4 by parity. So you can also look at, for instance, the 2-point function, just 2 points, x1, x2. What is the behavior when x1, x2 become very large? apart? Well, if it decays exponentially, it's called massive. The number there is the mass. Otherwise, well, it could be a power law or with some logarithmic corrections. And in this case, one would say that this is a massless critical theory. Okay. All right.
I was one, since you have, may I ask just from this mathematical ignorant question, what are observators?
That was the IFI.
Okay.
So terminology again.
Random variable in the probability language.
The thing you take the expectation of. Okay, so of course nothing I said makes sense. Huh? So try to do some mathematics. What you can do, which is quite natural, is to introduce what is called the ultraviolet regularization. One intuitive way to do it is to replace RD by a lattice of mesh small a, so AZD, and also this famous lambda, the volume finite box, volume cutoff. And if you do this, then RD only has a finite number of points. So that's great, because this becomes just we're integrating in Rn, so there's no problem. So the integral, the field will be a function, or rather the space of functions which are denoted by f, depending now on these cutoffs, is just R to the power, the number of lattice points in the box, just Rn. So in the previous formulas, what you have to do is to replace integration with respect to x in RD by just Riemann sums adapted to this lattice. If you see a derivative, you replace by a finite difference. Okay, and now you do numerical analysis. So the question now is, what happens to the measure which you define in this way, which is well defined when you take the limits where this lattice spacing goes to 0, you approach the continuum, and the box goes to infinity. So this is quite difficult. I'm not going to talk much about this. Just say that in order to do this, you usually have to let the parameters mu and lambda vary with the lattice spacing A. This is called renormalization. There is a tool to do this. You could say maybe that what I explained is a bit too much of a reduction, because I kind of said that what is interesting is the limiting object, those measures in the continuum. But you can also ask yourself the question, what are what's happening in the limiting process? Can you classify these type of limiting processes? It's kind of like trying to classify central limits theorem in a very, very general setting. And there is a tool to do this, which is the renormalization group. Okay, I'm not going to talk about this. I'm just going to focus on the question on the right, how to do the thermodynamic limit. Lambda goes to infinity. Ooh. Okay, so let's go back to the z of lambda. So z of lambda, now I'm going to work with the unit lattice, so a equal 1. And lambda for me is the same as the finite set of lattice points in ZD. So now I'm looking at an integral like this. So I have this phi, which is now a vector in R lambda. I'm integrating with respect to Lebesgue measure this thing. Okay, so that's the original model. If you ignore the lambda, what you have here is a Gaussian measure with covariance C, and this C is essentially minus Laplacian plus mu identity. And so this is a matrix, and in this particular case, when you include this mu here, you have an exponential decay of this covariance matrix. So that's quite nice. So this is called free propagator decay. And now I'm going to look at the pressure, so limit of log z over the volume of lambda. There is a slight change. It's not z, it's z tilde, because there is a factor which is the normalization of the Gaussian measure, but that's not very difficult. So I'm going to focus on this instead. So this is a normalized Gaussian measure with covariance C, and I multiply it by this. Lambda is small, and question what is this limit. So as David explained earlier, one particularly nice way to do this is to map this problem into the ones we saw yesterday, polymer models. So basically you want to write z of lambda as a sum over partitions of lambda of product of things which are completely factorized over the blocks of the partition. And these are those polymer activities or polymer weights. And okay. And for this, so this is what I called actually what we call the cluster expansion. So this is the first step. The second step is the Meyer expansion. Whereas I guess what Roman was calling the cluster expansion is what we call the Meyer expansion. But, oh well. Okay, so and for this,
I would call it polymer representation, because you represent it in terms of polymer.
Yeah, so it's just different terminologies again, more confusion, but that's how it is. So for this, I'm going to use this decoupling formula, which is the Brydges-Kennedy formula, and the idea is to try to decouple this covariance, as David was explaining earlier. So let's see what happens. Well, actually, I'm going to, just assuming that we know how to do this polymer representation. I mean, by now, we know how to compute the log and all that. Just quickly, there is this step of dividing by the amplitudes of the trivial polymers. Okay, so if your polymer Y, so a subset of the lattice volume lambda is a singleton, is only 1 point, and if also you have translation invariance, it's not really important, but it's nice. One way to do this is to put periodic boundary conditions. I didn't talk about that at all, but in this case, the amplitude of this polymer is a number which is pretty close to 1, at small lambda. So what you can do is to take the previous formula and divide by this constant at the power the number of sites you have. And in this way, you don't see anymore these trivial polymers. And so now you have a collection of disjoint polymers which don't have to fill everything. What is missed is filled by trivial polymers. So that's the difference with the partition. And they're disjoint, so they're different. So you can number them, and you can compensate for that by dividing by 1 over n factorial. They have this formula. So let's call this z tilde tilde. And of course, the Meyer expansion computes the logarithm of this and involves a coefficient, which is this Meyer coefficient. It has exactly the same structural form. It starts at 1 instead of 0. And, well, there is this thing here. And, OK, so what is this coefficient? Well, it's a Mobius function. So now let's talk about Mobius. More precisely, what is this Mobius inversion in which partition lattice? So let's take E a finite set. And so capital pi E less than or equal to is the partition lattice. I say that the partition pi 1 is smaller than pi 2 if I can obtain pi 1 by breaking the pieces of pi 2. All right, so this is a lattice, but not the same use of the word lattice. It's, again, so this is just a partial ordered set with the sup and inf property. So what is Mobius inversion? Quickly, well, suppose you have a function f from this set of all partitions, capital pi into R. A function g from the same set of all partitions into R is the Mobius inverse of f if, well, this formula holds. So it's kind of like saying that the vector f is the vector g times the triangular matrix which encodes this less than or equal to. And the Mobius function is the inverse of this matrix. So in this case, it's just product over the blocks of the partition, minus 1 to the mx minus 1, mx minus 1 factorial, and for a given, oh, this should be an x here. So for a given block x, this is just the number of blocks of the smaller partitions inside it. And this actually gives you the formula for the cuminance we saw earlier. Okay, so now let's do a refinement of this. So let's take a graph G on the vertex set E. And again, sorry for the confusion. I was taking in French, or ensemble. Espace. Okay, so espèce. So now I will consider pi E G. So there is this fixed graph, and now I'm going to throw away lots of partitions and only keep ones with a certain special property with respect to this underlying graph. Oops. And the property is that I want my partitions to be such that for any block of the partition, the induced subgraph on that block connects the block. So for instance, in this picture, we have in blue this graph on the set E, same thing here. This thing here is acceptable because if I look at this, for instance, this block of the partition, well, everything is connected only involving this edge and this one, which are inside the block. Whereas if you need to go outside and come back, that's not good. So this is not good. So I only keep the partitions which satisfy this. And again, this is a lattice which has a Mobius function, and the
What does this induce
Hmm?
You said
induce, you throw away everything which crosses boundaries of the
Which
partition.
components of the underlying graph?
Or I mean, well, sorry. I mean, if you're looking at a subset, you only keep the edges inside, which are completely inside the subset. Is that what you call induced? No.
Yeah. So the partition, it is on the vertex set.
Let me put the picture again.
What you mean is that the blocks must be containing the connected components of the graph.
Sorry,
The blocks must be inside the connected components.
No. Oh, okay. Let's go back.
Isn't it that you have an underlying graph and that
You have-
partition is acceptable if it is...
The graph is fixed, and now with respect to this graph, I'm gonna say a partition is good or it's bad. It's good if it's like this. It's bad if it's like this. What's the difference here? If I look at the block, in order to go from here to here, I need to go outside the block. I don't want this. That's all.
So what Mark said is correct. Each block must lie within a single connected component of the graph.
Not
No.
enough.
Restriction to a given block
You see-
is connected.
This block is. I mean, this property is true here, but that's not good.
It's like in that polynomial, right? So allowed partitions are those which are obtained by deleting some edges.
No, because, for example, if you add a triangle, you cannot keep only two of them because it is induced. It's a subset because you keep only the induced subgraph.
But it's a partition.
Okay, for any block of the partition, for any red thing, you throw away all the edges which are not entirely in that block. So that's what I call the induced graph, and I want this to connect that block for any block, or what I said earlier. If you phone next door, you don't want your connection to go through go through Dubai and come back.
That's one thing. So this
Yeah. Everybody's tired this morning. What's going on? Okay, so same notion of order. So I mean, the left-hand side is obtained from the right-hand side by breaking into pieces. Now, if you have these polymers y1, yn, which are subsets of this lattice lambda, I think we're in level 3 now, something like that. And if we look at E, the set of indices, we draw an edge.
Y1 through Yn are
subsets of lambda.
Of the underlying vertex set.
So it's some subset
Why
y1.
were you doing this abstract thing? Oh, I see. Now you're going to say how you were applying this abstract thing to your.
This is y3. So yeah, just to say, so if you have these polymers y1, yn, so subsets of lambda, you look at the sets of indices E, you draw an edge if there is intersection or if they are incompatible, and so this Meyer coefficient is 0 if G is not connected. Otherwise, it is the Mobius inversion of the Mobius function of this particular lattice, where 0 is the partition which has singletons and 1 is the one block partition.
But you haven't given us yet an explicit formula for this Mobius function.
No. But
Can you? It's
no, I'm going to focus on other things since this is what.
Actually, so unless the graph is a complete graph, it's complicated.
Anyhow, so just as an aside, well, this is also kind of related to hyperplane arrangement of certain kind. If you look at Cn, hyperplanes of the form, so if you have a vector of coordinates x1, xn, and you take two indices, this is a hyperplane, and you look at all the subvector spaces that you obtain by intersecting things like that. They again form a lattice. It has a Mobius function. So there is a whole theory behind this. And actually, there is also some nice combinatorial identities. I don't know if Alexander, are you going to talk about this afternoon? But there are some identities which involve sums over forests also. Okay. So the important property that we need, you saw that. It's basically you need that this coefficient is -1 to the n minus 1, sum over spanning trees of 1. And I think so there was this paper by Rota which proves this. Of course, Penrose 66 or 67, I don't know. 67, sorry. Okay, so I won't spend more time on this since Alan, Roman, and Aldo already did. And I'm going to focus on the decoupling, or what we call the cluster expansion, or the polymer representation. So start from this z tilde of lambda, integral d mu c of this. So as David explained, from a combinatorial point of view, the right way to see a good way to see the Gaussian integral is as exponential of a differential operator, which is essentially a Laplacian acting on the integrand, and then you take phi equals 0. And once again, between two things, you notice that there is a 1 hiding there. And so at first, you're going to say, well, if the sites x and y are different, 1 is in fact a new variable which depends on the pair, the unordered pair, t of xy. And if they're the same, then 1 is just 1. And so this is the evaluation of some function of a big vector which has, you have one variable per pair in your set lambda, where all the parameters are set to 1. And you want to compare with t equals 0, which corresponds to a decoupled situation where all the random variables are independent, as David.
Well, let me just ask you a question. Now your exponential Laplacian is acting on a function which is no longer a polynomial.
Yeah.
Does this thing make sense, or does it just give you a divergent formal power series in lambda?
Well, in this case, yeah, because it's not analytic. It's not analytic at lambda equals 0. You need lambda positive for this to make sense. But again, if this was a polynomial, and if you're doing formal power series,
But is there some way of interpreting this analytically? it nevertheless does make, if you don't expand in power series in lambda, this makes sense to apply this infinite order differential operator to this.
Well, that's maybe what David said. You run the heat you solve the heat equation, and
Okay, so it does.
It is analytic in phi. That's all that counts as far as this is concerned.
Okay.
yeah.
I think here you have to regard this though as shorthand for approximating the exponential by a polynomial, proving all your formulas and then taking the limit afterwards.
So as you said, you're running the heat equation with an initial condition that's the exponential, so it probably
Yeah.
makes sense.
And just so, just an aside, Vick's theorem basically comes naturally from a espèce, I guess, point of view. When you expand something like this, you have things which you could draw like this, d phi, and so you have a graph with the free propagator and the differential operators with respect to this vector phi acting on a whole bunch of phi's, and these guys want to select a phi to kill, and by summing over all possible ways of doing that, you have a natural sum over graphs. And Vick's theorem in this form, actually, as far as I know, is due to Isserlis. And he's a statistician and classical invariant theorist, and the paper is in Biometrica, I think 1909 or something like that. Okay, so now what is, once again, the Brydges-Kennedy forest formula. So E, a finite vertex set. I'm going to use the notation P sub E for the set of unordered pairs in this set E. So there is a cardinality of E choose 2. So T with an arrow is a vector, so a collection of variables, one for each pair. So it's in this R to the n choose 2. And suppose I have a function f from this R to the P sub E into R, and I use a notation 1 with an arrow for the vector which has ones everywhere, and this one for the zeros. And the Brydges-Kennedy forest formula really is a form of the fundamental theorem of calculus, which says that the value of this function at 1, 1, 1, 1, 1, 1 is the sum over forests on E. Here you have, for each edge of the forest, maybe it's easier to see what's going on here. For each edge of the forest, you have a variable, h. And so this variable is integrated between 0 and 1. What you have here is the derivative of this, the partial derivative of this function with respect to these of the variables which appear in the forest. And then you evaluate this at some kind of weight which is made out of these parameters h. How are these weights defined? Here I put AR because there is another normalization which has BK. So the AR normalization is the one with the minimum. So the rule is, okay, you look at any pair here, ij. If ij are not connected, this W is 0. Otherwise, it's the minimum of the path that you take to go from one to the other, as David explained. Okay, so for instance, from 3 to 5, it's the minimum of H2 and H3. Okay. And so application to the first step, to the cluster expansion. So I take my set of my abstract set E to be a lambda, the lattice. I apply this formula, and what I get is a sum over forests on lambda. product of these parameters, a Gaussian integration, except that the covariant has been modified by these weights, which means that couplings have been weakened with this rule of you go along the forest and you take you multiply by the minimum of the parameters h that you encounter. You have this differential operator product of Laplacians, which look, as David said, it's cxy, d over d phi x, d over d phi y, if the edge is xy, acting on the integrand, which is the original thing here. So, I mean, the lack of factorization comes from this, for this Gaussian measure, not this guy here. But the point is, this thing here factorizes over connected components of the forest. Okay, you can group things according to what are the connected components. So you have a sum over partitions, and when you sum over forest with that given collection of connected components, it factorizes completely component-wise. And what you get is some amplitude which depends on which set you're talking about here. And the formula is exactly the same as here, except that things are restricted to y instead of lambda, and you sum over trees, spanning trees instead of, I mean, trees which span y instead of forests. And now that you have seen the Kotevsky-Price type condition for convergence of the Meyer expansion, basically you can control everything that's going on here. Analytically, you can show that for lambda small, the sum of this complicated amplitude is, well, gives you a finite sum, even if you multiply by 1,000 at the power of the number of the cardinality of y. And the sum is where you impose that y contains a particular site. Okay. So if you show this, you can do what you want. And for this, you need two properties. You want this thing to decay. So that was the objection that I think you raised earlier. You want not only that the decay of this is with respect to the cardinality of y, but also at fixed cardinality with depending on how it spreads out. Okay, so I'm going to give you a one-line proof of this. No, not, sorry, one page.
It's a long line.
Sorry. Maybe. So let's see an example. Take this, so 4 sites, x, y, z, u. That's your set y. And you have a certain tree which connects it. You have this product of Laplacians. What are they? Well, it's just, well, if you put all the propagators, the c's, on one side and collect the differential operators, well, you have exactly this. Okay, so you have one propagator per line. And remember that these things have exponential decay, so they look like exponential minus m, and here the sum of the distances in the tree. So that's why this notion of Steiner tree is important. Okay, and here you have basically, you look at each vertex and you take the derivative, how many times? Well, the degree of that vertex in the tree. And what do you do with this? You hit the exponential lambda phi 4. Okay, so you can basically look at this side by side. Well, it's easy to see that if you look at this, for instance, point z, you have this, these differentials. Well, the first time you're going to apply these differentials, they have no choice. They have to hit the exponential, so you get a factor of lambda. By this mechanism, you get a small lambda per site, and lambda is small. The vertex degrees are denoted by, well, dx, dy, etc. So 1 and 3. Then you have to sum over all ways of performing the derivation. So basically, you have to see how many terms you get when you apply this. And this is basically bounded for each vertex by the degree factorial. It's not very hard to do. You have to imagine yourself, you're doing it and you're recording everything you did. Basically, either you go hit the exponential or you go hit some vertex which was initially produced by a previous derivation, so you just have to find which one it was, and summing over this, you can bound the number by this d factorial, essentially. This twiddle thing is because I don't care about constant to the d, or constant to the number of cubes, because I have a small constant per site, so I can beat these, no problem. But factorials I have to be careful about. There is a nice bound on the Gaussian integral one gets. If you have this Gaussian measure and you have some monomial, so product over the sides of phi of x repeated mx times, well, this is smaller than product of these are called local factorials. So it only involves the multiplicities at each point independently, although the Gaussian measure is couples everything. So this argument is due to Gleam, Jaffe, Spencer, I think. They proved this, but I think for an exponent of 1, and Ekman, Mania Senior, I think noticed it was better than that, no? I think in the appendix up here. I saw that. So basically, you get products of factorials of the degrees, and you can beat this by extracting a little bit of the tree decay. In one dimension is because, well, suppose you have a tree which you have this vertex, and it has a pretty large degree d. That means that you go fetch one, second one, third point, but they cannot be the same, so they have to go further and further. And so if you have exponential decay, even a small one, this is something like epsilon d squared over 2, and this beats d log d, so any factorial, no problem. And then once you have done this, basically you just have to sum over the set y fixed. I mean, you have to. It has to contain a certain point. You have to sum over trees on this set y. So these are pin and sum type arguments. One way to do it is to. So this is from the Rotau, the Penrose identity, the bound in terms of trees with respect to intersection. So what you have to do is to sum over the number of these guys, 1 over n factorial. Actually, you want to commute. You want to sum over trees before you do the sum over the points in your subset. And well, once you do this, using the tree decay, you can sum over where is the point y5, knowing where this guy is, where is the point y3, knowing where this one is, etc., all the way up to the point which the origin. I mean, everything was supposed to contain a certain fixed point in the lattice, and so this just gives you a constant to the n number of trees, Cayley's theorem, n to the n minus 2 divided by n factorial. So this is perfectly summable. It's a bit fast, but everything is here.
When you talk about volume effect, you should actually have an exponent depending on the Euclidean dimension, say.
Yeah, so this doesn't work if you were in a better lattice, or yeah, so you're in finite dimension.
Like degree to dimension plus 1 over dimension. That
Yeah.
one is only the exponent for d equal 1 in the sense. D in the sense of dimension, not of the d.
Yeah, sure.
But anyhow, it's
But
bigger
it doesn't
than
work. Yeah,
bigger than
it works
everyone.
less and less if you increase the dimension where you're.
So you're using here that you have one fixed polymer and then these other guys
There is just.
overlap the first one?
There is, sorry, I'm doing the Koteski price thing here. So there is one polymer, so there is just one set included in lambda, and it has to contain, let's say, the 0, the origin.
No, I mean at this volume effect that you did.
Mm-hmm.
Is that based on the argument that you have one polymer and a bunch of others that overlap the first one but don't overlap each other?
No, there is only one polymer in this whole picture.
Oh.
What is decreasing is the propagator.
Yeah. So there is only one polymer here, set y, and these are the small y's, not capital Y. Maybe I should have changed. Sorry. Yeah, these are points making the set y. So I number them. I compensate for the numbering by 1 over n factorial. Once I have a numbering, then I can commute the sum here because I can transport the tree structure on the abstract set of labels instead of the set of points in the lattice. And once I do this, then I forget that these points have to be disjoint, different. I just use this argument, gives me constant to the end.
For this volume effect, the key thing was that these points are different.
Different,
So
yeah.
that if there are a lot of them, some
Yeah.
of them have
You have to
be
go
rather
fetch
big.
them further and further, and the exponential decay beats that. Okay. How much do I still have for the 1001 proofs?
12 minutes.
Okay, so we'll do proof number 1, proof number 2 until exhaustion. Okay, 1001 proofs of the Brydges-Kennedy formula. So again, Mobius inversion. So set E, set of pairs PE. This time I go back to the full partition lattice. There is no underlying graph. But I introduce variables for each pair. So for each edge in the complete graph. And I'm going to take a special function for which I'm going to do the Mobius inversion. So it's product over the blocks of the partition of some capital F. And what is this capital F? It's exponential. I take for this block the sum of these variables where the pair has to be entirely in that block. Okay, so this is well defined in the algebra formal power series in the U's. And if I do the Mobius inversion for the small f in the partition lattice, I get a new function g of pi, which is a product over blocks. And there is a naive, I mean, as far as the purpose of what I explained earlier, proving bounds, formula for this where you have the sum over all connected graphs of e to the u minus 1. So this is not good to do analysis. There's too many graphs.
All graphs, not induced
Yeah,
subgraph.
yeah. This one is easy to write, but it's not good to do analysis with. And maybe I should mention the literature. That's probably a good time to do it. So there's too many graphs, and so in order to prove analytic results on these quantum field theory kind of models, you need resummations in terms of trees. So there was this Gröneveld, Roman was talking about Penrose, which actually was before, maybe, I don't know. There's this paper by Rota. In this context, really it starts with Glim, Jaffe, Spencer in 73, 74. And then there were later improvements, simplifications. The original paper, I think, was reputed and inaccessible. So there is a formula due to Brydges and Federbush, Malishev, Minlas, all these guys. I'm sure I forgot some people, and I apologize if we did. But I'm going to focus on result contained in this paper, Journal of Statistical Physics. This is not the volume number, it's the year. And you're going to hear about some of the other stuff here at this workshop later. So first proof, differential equation with quadratic nonlinearity. This is the original proof, Brydges-Kennedy 87. So we start with this g of x, sum over all connected graphs. Again, when you see nothing, there is a 1, and when there is a 1, there is a t. And so you put a t there. And look at the infinitesimal variation of this with respect to t, and find a differential equation for this. And you have to find a differential equation for the collection of all these things where you look at all subsets x in your set E. So the method is, well, write differential equation. You're going to find the nonlinear with a quadratic nonlinearity. Well, write the integral form of that, iterate, you generate trees, try to solve, find an explicit formula for that. This is what David and Tom Kennedy did. And I think there was some inspiration from Wilson and Proshilsky type. Yeah, so there is an equation in the renormalization group which has this similar type of pictures, which produces what are called Galavotti-Niccolo trees, which have also been studied by Feldman, Hurd, Rosen, and Wright. Hurd. I'm not going to talk about this, but I should mention it. And here's how you get this equation. So g of tx, well, you sum over simple graphs, which connect x of e to the t ul minus 1. Expand this. So what you're going to get is a sum over multigraphs. And with obvious notation, so m is a multi-index. For each edge, you take it as many times as you want. So if you collect here with respect to the support, you get exactly this. So you have a sum over multigraphs of this thing. You take the derivative. That means that you're choosing one of these t factors. That means you're choosing one of these lines in the multigraph. And you get this, again, with obvious notations. You have to sum over multigraphs, choosing a line in it. Well, take it away. And there is two cases. Either the multigraph without the line is already connecting everything, so you're in this situation, or it doesn't. And you have this situation, and you collect the two terms, you have an equation like this. Okay, so dg over dt, this is the linear term, and this is the nonlinear term. Maybe, okay. Well, so if you can find a clever explicit expression for this, then, well, this is equal to the original one by a uniqueness argument of the solution of this equation. But so the explicit formula found for by Brydges and Kennedy in the original paper is a sum over spanning trees on x, product of integrals over interpolation parameters. Well, you have these things which appear explicitly exponential, what we had before, but with a weakening factor here, which is actually 1 minus the max of the h parameters on the path. I prefer to work with the min. All right. Okay, there is now a second proof. Well, I didn't really complete the proof, but another way to do this is by some complicated partial fraction decomposition, which was in a paper by myself and Vincent Rivasso. Okay, so f of 1 is exponential the sum over all pairs contained in E of the variable attached to that pair UL. And one can write this as a sum over forests, something like this. Example, take E equal 1, 2, 3, 3 points. You have 3 variables, U1, 2, U2, 3, etc. What we're doing is to express this sum here as a sum over forests. And the contribution of these forests. So what do we do? It's hard to have everything on the same. Okay. In this case here, there is nothing in the forest. So there is no integration, no parameter. There is no factor here. And nothing is connected. So everything here is 0. So it's just 1. Now, if we have this forest here, we have only one parameter between 0 and 1. We have the variable corresponding to the edge in the forest, U1, 2. And you have an exponential here with weakening factors. So between 1 and 2, we have H1, 2, and the other ones get 0. And this is just E of U1, 2 minus 1. Okay. A little more complicated, not so much. Now, if you do forests which have actually trees this time, which have 2 edges, you have 2 parameters, some complicated thing here. So you see that here you have explicitly the variables corresponding to the edges of the forest, some exponential, and here you have this minimum rule. Okay, so between 1 and 3 is the minimum of the path. And well, you do the integration explicitly, and you find something. What is the pattern here? Okay, No.
Okay.
No,
Second one.
sorry. I have to go fast. If you have a non-ordered forest, there is a version of this which involves ordered forest, so a sequence of edges L1 to LK. So it looks like this. Basically, what you do is instead of integrating over the whole cube, you break it into simplices. So you have a sum. You have an integration now over a simplex like this. With decreasing parameters, you can transport the permutation to have also an order on the forest, which you didn't have before, and you have a sum like this. And what we have to prove is that, well, this identity holds. What is the rule here for this weakening parameter is that it's 0 if I and j are not connected at all by the whole thing, the whole forest. And it's h sub nu if, starting from left to right, I and j fall in the same component when you have included all the edges up to the nth one. Okay, so if you're connected at stage nu but not at stage nu minus 1, you get as a reward the h nu factor. Okay, well, you can then do some calculations, change variables, write h equal this, do the integration explicitly. You have some partial fraction, and also the exponentials there, just give them a name. It's new variables v, l. And now we just do algebra. And the algebraic version, again, of this identity is this. I won't have time to show the proof, I think, of this, but at least you should see the formula. And it's now showing the Brydges-Kennedy formula is the same as showing this identity here. So on the left-hand side, we have the product of the v variables over the complete graph. And here we have sum over ordered forests, something which involves both the v's and the u's. So here we have the product of the u's which appear in the forest. There is no, the length of the forest can be any length r we want. There is these things here which I call a nu f. So this is, so the forest goes from 1 to r. Nu is some intermediate stage. So at stage nu, I just keep the beginning segment. And I look at what has been connected, what are the connected components at that time. And I sum over pairs which are in a block of in one of these connected components of the variable u. And here I do the same thing, but with products of these. Okay, this complicated thing, I think I won't have time to talk about the pure algebraic proof of this. Because there is a, actually, so there is another, so there is an algebraic proof of this by induction on the size of the set E, which kind of looks like a deletion contraction argument a little bit. Or, there is also a proof of this using matrices made of Stirling numbers and Kronecker products of these things. I mentioned this problem to Vincent Laforgue, and he also came up with a very nice proof which involves minimal decompositions of permutations into transpositions which make forests. So there's a whole lot of proofs for this. And finally, the one which I think is maybe the simplest, I should have started there. So it's a Taylor expansion with stopping rules, and it involves iterated integrals. There is this formula here which involves these variables u. Actually, it's equivalent to the general version where you take any function. Why? Well, if this is true, then this is true. That's just by specialization. Take the function of this form where you put the t in front of the variable u in the exponential. But if you know this, then you can prove this, because you apply this to differential operators d over dtl. And if you know it for differential operators, then you know it for any function, because exponential of derivative is translation. Okay. So now in this point of view, this is really a theorem, fundamental theorem of calculus, plus epsilon. And so I call this the Taylor Brydges-Kennedy formula in the ordered forest version. So what you want to show is that a function of all the parameters set to 1, sum over ordered forests, integration over this standard simplex, the derivatives of the function with respect to the variables which appear in your forest, and this weight, and recall that this weight now between 2 points I and j is 0 if these points are never connected, and it's h nu if I and j are connected exactly at time nu. You imagine yourself, you throw the edges one by one, like in an animation by Xavier. When I and j are connected, that's when you put the parameter. And the proof of this actually, so we, I think we first wrote that in an article by Vincent and myself in '97, but actually it's based on a earlier idea, I think, of, I mean, we were talking about that in the summer of '94, I think, by Knorr, yourself, and Jack. And so the idea is to do this, take f of all the variables at 1. Well, say that, again, 1 is some other variable set equal to 1, so h1, and do the fundamental theorem of calculus, so it's the value at 0 plus the integral of the derivative. Chain rule, or, I mean, you have to choose where you put the derivative, so you choose which first edge you produce, and the function is still evaluated at everybody equal to h1, but then you say, well, I am going to keep track of where was the edge I have chosen, so it's a particular entry in my function. This one stays equal to h1, I'm not going to touch it. Everybody else is now a new variable, h2, which happens to be set equal to h1, and I continue this way. So the rule is to freeze edges or pairs which correspond to a pair of points which has already been connected. And so the nice thing about this is that it generalizes to hypergraphs. So both Vincent and I, and also Gilles Poirot, realized that this opens up lots of generalizations, hypergraphs, p-particle irreducibility. You can do this, and okay, I'll stop here. So maybe I should do the question.
In a concept, it's somehow like if you take the top polynomial for perforation and you do shellability in the sense of only forest. Shellability in the sense, well,
what
I
is
don't
that?
know. We have just a product of V per edge, and we are having at the end an expansion only over forest. That's like shellability of top in percolation.
I don't know.
No, well, that's not a good question. Sorry.
Can I make a remark about that? I mean, shelling is a way of decomposing these, associating connected graphs to trees, but it has these arbitrary choices. And the beautiful thing about this formula is that it somehow
Averaging over choices.
it averages over choices to make everything beautifully symmetric. So it's really much nicer and more canonical.
It looks like the variable sigma induces an ordering and then a choice. And so integrating over sigma is like summing over.
Yeah.
So I was making the remark that it seems to me that this thing doesn't fit exactly into the categories of operation that you used on species, and that it maybe perhaps there is a kind of interpolation or Taylor operation between species, on which this is a simple example in case of graphs and trees, but which might be more general. And I would like to see perhaps that this can be developed into further examples of picking a sort of smaller, simpler structure in a larger one. But of course, since I don't know anything about species, I can't say.
Yeah.
So Okay, you're going to inherit the question that I didn't do today. The use of the polymer representation, because the end product is this polymer representation.
Yeah.
Now, usually I associate that with proofs of analyticity, but these are out in this case. Okay,
Yeah.
So what are the applications? What do you do with that polymer representation? What questions you ask?
You do the.
In lambda, they cannot be analytic.
You do
But
the.
it can be analytic in e to the minus lambda pi form.
Just to follow up
It's to do the thermodynamic limit, but for a small lambda.
follow up on Vincent.
So here you're not, excuse me, so you're not expanding around the situation where everything is independent, so the product measure, but you're expanding around the Gaussian measure, which couples things, so you still have to.
And you expand only in positive parameters, in the space of positive parameters, even e to the minus lambda or lambda.
You definitely need the positivity of lambda for this
Not
to work.
polydiscs anymore.
No. Yes.
But you can, analyticity and lambda in the wedge region or something.
So I just wanted to follow up on Vincent's question. So you're doing this interpolation with edge weights on the complete graph, Kn, right?
Yeah, in the end, yeah.
But it could just as well have been any graph, right? Because couldn't the edge weights on the non-edges just be set to 0?
Probably, yeah. You would do that, I guess.
Okay. So then a possible generalization of the type Vincent was seeking was, instead of a graph, put a matroid with edge weights on the elements of the matroid, and instead of Forrest, put independent sets in the matroid.
Mm-hmm.
That might be the right combinatorial. Because, for example, the Penrose lemma generalizes that way immediately, that this partitionability of the connected spanning subgraphs of a graph is actually partitionability of the independent sets or spanning sets of a matroid. So maybe that's the one possible direction to generalize. Bill knows the answer already.
No, I just think maybe you could even go to polytopes, the simplicial complexes. And
Right.
Build simplicial complexes randomly somehow.
Right, but it may not go to all simplicial complexes. It may be partitionable simplicial complexes.
There is a nice thing if you want to get the integral over the factorization over connected components, and you work with the ordered forest, then you have this integration over the simplex. So then there is a coupling between the parameters, because one has to be bigger than the other in the sequence, even within involving different connected components. So there is something like the shuffle product that you need to do to factorize things. So summing over all possible ways to take an ordered tree on this component, and make an ordered forest.
Let's thank the speaker again.